My name is Mohammed Layiq Sediqi, and in this part of our journey together, we finally turn and look straight at the heart of the Holophase model. How one hidden rhythm gives birth to time, space, and motion all at once. If you have been with me from episode 1, you already know the path we have walked. We started from life itself, from 4 billion years of blind experiments that every cell has been running against reality. Then we looked at the story that modern science tells about the world. Everything is energy in spacetime. We gently questioned that story. We introduced the idea of a single underlying phase, the holophase, as the true substrate. We spent a whole episode dethroning energy from its sacred place as the stuff of the universe and reinterpreting it as a powerful but secondary bookkeeping language built on something deeper. In the previous part of episode 5, we did something different. We did not argue yet. We listened. We listened to thousands of years of human struggle with 3 words: time, space, motion. We walked from ancient myths to philosophy, to Newton, to Einstein, to quantum theory, to today. We saw how each generation tried to say what time is, what space is, what motion is, and how each answer solved some problems but left others bleeding. Now, in this part, we begin the turn. We are going to use Holophase as a new lens and ask a very simple but very radical question. What if time, space, and motion are not 3 separate ingredients poured into the universe, but 3 different ways of reading one underlying pattern? Imagine you are listening to a piece of music. You can talk about that music in at least 3 ways. You can talk about the tempo, how fast the beats are coming. That is like time. You can talk about the melody shape, how high or low the notes are, the shape the tune makes if you drew it as a curve. That is like space. You can talk about the groove, how the music makes you move, how your body starts to sway or dance across the room. That is like motion. 3 descriptions, 1 song. You have not added anything to the music when you say it is at 90 beats per minute. The melody climbs, then falls. The rhythm makes my feet move. You are just choosing different ways of reading the same underlying structure. Holophase says, reality itself is like that. Underneath everything, the universe is written as a vast, continuous pattern of phase, a giant, living rhythm. Time, space, and motion are 3 ways that rhythm becomes visible to us. They are 3 views or projections of one and the same underlying order. This sounds poetic, but it is much more than poetry. It is a precise scientific claim that can be tested, supported, or broken by experiments. And that is exactly what we will keep doing. We will always ask, how would we falsify this? What observation could prove that this picture is wrong? To make this idea real, we are going to move slowly and carefully. In this part, we will do 3 things. First, we will build an intuitive image of what I mean by one underlying rhythm. No equations, just pictures you can hold in your mind. Second, we will show step by step how each of the 3 big words, time, space, motion, can be read off from that rhythm in everyday situations. Third, for each of the 3, we will talk about simple but powerful tests that anyone, from a curious student to a professional physicist, can use to see whether this one rhythm, 3 faces idea fits the world or fails. Let us start with the underlying rhythm itself. When I say phase, do not think of some mysterious symbol floating in a textbook. Think of something very familiar, a cycle, a turning, a repeating pattern. Picture a small dot moving around a circle, like the hand of a clock, but not just in one device on your wall. Imagine that for every point in the universe, there is, in principle, a little arrow that tells you where in the cycle the underlying rhythm is at that location right now. The arrow can point anywhere around the circle, but its direction only matters relative to other arrows. You will never see these arrows directly. You will never see the pure phase itself. Nature does not hand us the raw number that says the phase here is exactly this. What we see, always, are differences and changes. We see how the phase at one place differs from the phase at another place. We see how the phase at this moment differs from the phase a moment later. We see how patterns of phase shift, interfere, and slide. From those differences, we build our world. To make it more concrete, imagine a huge stadium full of people holding tiny lights. At first, they are all random. Lights flicker with no pattern. Now imagine that somehow, over time, the crowd learns to flash their lights in a coordinated way. In one part of the stadium, they are bright. A little further on, they are dimmer. Somewhere else, they are dark. And this pattern slowly moves around the stadium. If you watched from far above, you might see something that looks like a wave of light moving around the ring of seats. You would see bright and dark bands, patterns shifting in time. You could stand in one spot and measure how often the brightness at your seat peaks. That would give you a frequency, a sense of time. You could look across the stadium and see how far apart the bright bands are. That would give you a wavelength, a sense of space. You could track how fast a bright band moves past different seats. That would give you a speed, a sense of motion. But underneath all of those measurements, what is really happening? Individual people are turning their lights on and off according to some common rhythm. The phase at each seat is simply where in the on-off cycle that person is at each moment. The wave you see, the time pattern you feel, and the motion you track are all readouts of this deeper coordination. Now replace the stadium with the universe. Replace the people with tiny degrees of freedom of the holophase. Replace the lights with the local phase at each point. The holophase claim is that time, space, and motion are like the frequency, wavelength, and wave speed that an observer reconstructs from the way this deeper phase pattern behaves. Let us now look more closely at each of the three. We begin with time. Most of us think of time as something separate, a kind of invisible river that carries everything forward. But what do we actually do when we measure time? Think of every clock you know. An old pendulum clock counts swings of a weight, left, right, left, right. A quartz clock counts the tiny vibrations of a crystal driven by an electric field. A digital watch counts ticks produced by an oscillator. An atomic clock counts certain transitions in atoms that repeat at an extremely steady rate. Different technologies, same idea. Find something that cycles regularly and count its cycles. At root, every clock is a phase counting device. It tracks how far along a cycle some oscillating system has moved. It does not know what time itself is. It only knows how many times has this process gone round and round. Holophase takes this simple, concrete fact seriously and pushes it all the way. It says, when we speak about time in physics, we are always, whether we admit it or not, talking about how much phase has advanced. Time is our name for the rate at which the underlying rhythm turns. From this point of view, a day is not a mystical unit handed down from heaven. It is how long it takes the Earth to rotate once relative to the Sun. A second is not a divine grain of time. It is so many oscillations of a given atomic process. You can change the unit, you can choose a different cyclic process, but you always come back to the same structure, count cycles of something. Here is a very simple falsification test. If Holophase is right, then any real practical time measurement must boil down to counting cycles of some process, which in turn can be described as changes in the phase of some physical system. So ask yourself this: can we design a clock that does not depend on any repeating pattern? A clock that does not count swings, pulses, transitions, or cycles of any kind? At first, this sounds trivial. You could say, I will just mark time by how far a stone falls under gravity. But even that, when you describe it carefully, becomes a certain pattern of motion, a curve that can itself be related to periodic standards. In real physics, when you try to make a practical, precise time standard, you always end up choosing some oscillator, a pendulum, a crystal, an atomic transition, a resonant cavity, or something similar. If someone one day proposes a method of measuring time that truly cannot be described as counting phase changes in some system, that would be a serious challenge to the holophase view. Until then, the fact that all our clocks are secretly phase counters is a strong hint that time as phase change is more than a poetic metaphor. Now let us turn to space. What do we actually do when we measure distance? In everyday life, you might pick up a ruler or a tape measure and line it up between 2 points. But think more deeply. What makes the marks on that ruler meaningful? Why do we trust that the spacing between centimeters is the same along its entire length and the same from one ruler to another? Historically, length standards were tied to physical objects, a metal bar, a rod in a lab. But those are not very stable. Temperature, bending, aging can change them. Modern science does something far more interesting. It defines the unit of length in terms of how far light travels in a certain amount of time. Light is a wave. It has a certain frequency, a certain phase pattern. By fixing the speed of light as a constant and defining the second in terms of cycles of a specific atomic transition, we effectively define the meter in terms of how much phase a light wave accumulates between 2 points. In simpler terms, distance has become how many wave crests fit between here and there, or how much phase change a standard wave experiences between two locations. Even in simpler, hands-on experiments, this is how we often measure space. In radar, you send out a pulse and measure how long it takes to come back. In interferometry, you compare the phase of waves traveling along two paths. In holography, you reconstruct the three-dimensional shape of objects from interference patterns, which are nothing but spatial maps of phase differences. Holophase says this is not an accident. We keep coming back to waves and phase differences to measure space, because space, as we experience it scientifically, is a way of organizing phase differences across locations. The geometry we reconstruct is the pattern of how the underlying rhythm varies from place to place. Here is another simple falsification test. If holophase is right, then any sufficiently precise fundamental measurement of distance will rely on comparing phases of some propagating signal or on counting how many cycles of some reference pattern fit between 2 points. So, again, ask, can we define and measure distance in a repeatable, high-precision way without any mention of waves, signals, or phase-like patterns? You might say, we can just lay rods end to end. But even that relies on our confidence that the rods themselves were calibrated using methods that, somewhere down the line, connect to wave-based standards. In modern metrology, this is not optional. The best rulers in the world are made of phase. If one day someone produces a completely different, non-phase-based method for defining and measuring length that outperforms wave-based methods and cannot be rephrased in phase language, that would be a strong point against the holophase picture. Until then, the dominance of wave-based distance measurements is one of the quiet but powerful pieces of evidence that space as phase pattern is not just a story I made up. Now we come to motion. Motion is so familiar that we often forget how strange it is. We say, the car is moving at 60 kilometers per hour. The planet orbits the sun. The electron is traveling through the detector. And it feels obvious. Something is in motion. But what are we actually tracking when we say that something is moving? Return to the Stadium of Lights. You see a bright band moving clockwise. What moved? The people stayed in their seats. The stadium did not rotate. What changed was which people were bright at each moment. A pattern moved. Or think of a wave on the surface of the ocean. A crest seems to travel towards the shore. If you follow an individual water molecule, it mostly bobbles up and down in place. The movement you see is the progression of a particular phase pattern across the surface. Even a simple sound wave in air is like this. Your eardrum is set into motion, but the air molecules mostly vibrate around their positions. A region of higher pressure sweeps through the room, but that region is not a group of permanently marked molecules. It is a phase pattern in their collective oscillation. Holophase takes this observation and again pushes it all the way. It says, what we call velocity, what we call motion, is a way of describing how features of the phase pattern move relative to our chosen frame. When we say a particle is moving, we are really saying the phase features we use to track that particle change in a way that corresponds to a certain speed. The famous relation between frequency, wavelength, and speed in waves is an example of this. If you know how quickly the phase changes in time and how quickly it changes in space, you can infer how fast the pattern is moving. Here is the third simple falsification test. If holophase is right, then any measurement of motion, of speed, or velocity in a deep physical sense must be expressible as how fast a phase feature moves relative to another phase feature. So ask, can we build a speedometer that makes no reference, explicit or hidden, to any repeating process, any phase pattern, any timing signal, any spatial pattern? The speedometer in your car, for example, is ultimately tied to the rotation rate of the wheels, or to the rate at which pulses pass through a sensor. Radar guns measure speed by looking at frequency shifts in reflected waves, a pure phase effect. Navigation systems compute velocity by comparing timing signals from satellites, again comparing phases of clock signals. If someone can produce a physical method of determining velocity that is both precise and cannot be described in terms of phase changes of anything, that would hurt the holophase view. If not, the fact that all real speed measurements are wave-based or clock-based becomes yet another quiet piece of support. We can now put the three pieces together. Time, how fast the phase changes at one place. Space, how the phase differs from place to place. Motion, how features of the phase pattern travel through those differences. One rhythm, three phases. To make this even more tangible, Let me give you a simple, everyday style experiment that carries all three at once. Imagine you are at the beach, looking at waves rolling in. You stand in one spot and count how many crests pass you in a minute. That gives you a sense of frequency. That is your time readout. You look along the shore and estimate how far apart the crests are from each other at one moment. That gives you a sense of wavelength. That is your space readout. You throw a small floating ball into the water and track how fast a crest carries it towards the shore. That gives you a sense of wave speed. That is your motion readout. Three quantities, all coming from one underlying waving pattern of the water's surface. In Holophase, the entire universe is like that beach, but in a far richer, higher dimensional way. The water surface phase in this image is replaced by the holophase itself. The patterns in that deeper phase produce what we call particles, fields, forces, and so on. Time, space, and motion are our human names for three particular kinds of measurement we make on those patterns. What makes this more than an analogy is that our best physical theories already treat many things in exactly this way. Quantum mechanics is built on wave functions whose phases control interference and probabilities. Electromagnetism is written in terms of fields whose phases encode polarization and propagation. Even general relativity, in many formulations, can be expressed in terms of how waves propagate through curved geometry. Holophase simply takes a bold step that these theories hint at, but do not fully commit to. It says, stop treating phase as a secondary decoration on top of more real entities like energy or spacetime. Treat phase itself as the primary ontic substrate. Then show, carefully and experimentally, how all the other quantities we care about can be reconstructed as encoders of phase and its derivatives. In later parts of this episode and in future episodes, we will start to unpack what derivative means in everyday terms and how different orders of change in phase give rise to the rich zoo of physical concepts: frequency, wave number, curvature, flux, stress, and so on. For now, at this introductory level, I want you to carry a simple picture and a simple attitude. The picture is that of the giant invisible stadium of lights, a universe-wide pattern of coordinated on-off rhythms. Time is how fast the pattern flashes at one point. Space is how the flashing pattern varies across the stadium. Motion is how identifiable features of that pattern slide across the seats. You never see the raw phase itself. You only ever see the differences. Brighter here than there, earlier here than there, a crest arriving now instead of later. From those differences, you reconstruct the illusion of solid objects moving through an external container of time and space. The attitude is scientific humility combined with boldness. Holophase does not ask you to believe this because it sounds beautiful. It asks you to test it, to look at your clocks and rulers and speedometers and experiments and ask, are these secretly just phase counters? To examine the history of physics and notice how often our deepest equations talk quietly about waves and phases, even when our words talk loudly about energy and spacetime. Before we close this part, let us slow down once more and walk through three very down-to-earth examples that you can mentally rehearse whenever you want to feel the dimensional expression of phase. First example, a simple kitchen timer. Take one of those mechanical timers that you twist to set the time for your oven. Inside, a spring unwinds and a little gear train advances a dial. Often there is also a ticking sound. Every tick is a small movement of some internal wheel. That wheel does not simply slide forward, it rotates. Its position repeats over and over as it goes through its cycle. If you could shrink yourself down and ride on one of the geared teeth, you would experience time as, how far around the cycle have I gone? The ticking you hear is your ear being struck by a repeating pattern. You might set the timer for 10 minutes, but what that really means is, after so many turns of this internal phase, I will ring. You can already see all three dimensions hiding in this little device. The rotation angle of the gear is a spatial pattern around the circle. The rate at which it turns is a time pattern. If you painted a dot on the gear and watched it through a tiny window, the apparent motion of that dot around the circle would give you a speed. One rhythm, three faces in your kitchen. Second example, a city of synchronized traffic lights. Imagine a long straight road in a city at night. At each intersection, there is a traffic light that cycles through green, yellow, red, green again. Suppose the city engineers have synchronized the lights so that if you drive at exactly the speed limit, you will hit a green wave. Every light will turn green just as you arrive. What is happening underneath this convenient trick? Each light has an internal phase, some number between start of green and end of red. The engineers have adjusted the relative phase offsets between intersections so that the pattern of green bands appears to move along the road at the speed of a typical car. To you, as a driver, this feels like a pure space-time effect. You see a series of positions along the road, each with a light that changes in time. You adjust your motion to fit that pattern, but the whole thing is built out of phase, where each light is in its cycle, how those phases differ from place to place, and how the apparent wave of green sweeps down the street. Here too you can think of direct tests. Change the phase offsets and the pattern of go and stop in space and time changes, even though the underlying cycle period of each light is unchanged. In holophase language, you have changed the spatial structure of the phase without changing its local time cadence. You are literally playing with the dimensional expression of a hidden rhythm. Third example, global navigation. When your phone uses satellite signals to tell you where you are, it is listening to very precise clock signals sent from multiple satellites in orbit. Each satellite carries atomic clocks that emit regular ticks. These ticks are nothing but extremely stable oscillations, phase cycles of particular physical processes. Your phone receives those signals, compares the times at which the ticks arrive from different directions, and solves a geometric puzzle. Given these phase differences, where in space must I be? Out of phase comparisons in time, it reconstructs location in space and motion over time. There is no little tape measure reaching up to the satellites and back. There is no glowing substance of pure energy painting a grid. There are just carefully synchronized rhythms and a clever device that interprets the differences between those rhythms as coordinates in a three-dimensional world. From the holophase point of view, this is not just a clever engineering hack. It is a glimpse of the deeper structure of reality. It shows you that what we call here and there, now and later, moving and at rest, are operationally built from relations between cycles. Phase differences, phase rates, and phase motions are the raw material. Time, space, and motion are the names we give to consistent ways of reading that material. This also gives us another layer of falsifiability. If the dimensional expression view is right, then as our instruments improve, our most precise descriptions of time, space, and motion should increasingly be written in terms of underlying phase relations and their changes, not in terms of independent absolute containers. And this is exactly what we see in practice. The best time standards in the world are defined by atomic phase cycles, not by some abstract cosmic clock. The best distance standards are defined by how far light, a phase-structured wave, travels during those cycles. The best velocity measurements use Doppler shifts, time of flight, and phase tracking, not absolute reference rods. Let me emphasize again. None of this means that our ordinary language about seconds and meters and speeds is wrong. It means that these familiar quantities are faces of a deeper actor. They are like the shadows that one solid object casts when you shine lights from different directions. Shine a light labeled time on the holophase, and you get durations, how long between cycles. Shine a light labeled space, and you get distances, how much phase changes between locations. Shine a light labeled motion, and you get velocities, how fast recognizable features drift through those patterns. The shadows are real, you can live in them, you can build engines, rockets, computers, and cities using the language of time, space, and motion alone. Humanity has done so brilliantly. Holophase simply invites you backstage to meet the actor that has been casting those shadows all along. In the next parts of this episode, we will begin to coordinate this intuitive picture with the more formal side of the theory. We will see how the basic expressions of modern physics already hint at this dimensional unity, how the same underlying phase structure gives rise to what we currently treat as separate pillars: kinematics, geometry, dynamics. We will also refine our falsification tests. We will not be satisfied with vague statements like everything seems wave-like. Instead, we will outline concrete experimental patterns where a truly phase-based ontology makes different predictions or demands tighter consistency than an energy-based, spacetime-based, or particle-based picture would naturally demand. For now, take a breath and notice where we are. In a short series of episodes, we have moved from life's desperate need to model reality to the rise and dethroning of energy as the supposed substance of the universe, to the introduction of the holophase, and now to this central idea that time, space, and motion are not separate furniture in the cosmic room, but a single musical phrase heard in three different ways. If this idea feels too simple to account for the complexity of the world, that is understandable. The history of science shows again and again that the deepest structures are often the simplest to state and the hardest to fully absorb. All life comes from cells. All matter is made of atoms. Energy is conserved. Each of these is a short sentence with enormous consequences. Time, space, and motion are three readouts of one underlying phase, belongs in that family. In the following parts, we will earn that sentence fully. We will show how it integrates with relativity, with quantum theory, with field theory, and with the messy reality of experiments. Because if this picture survives your best attempts to break it, then it is not just my offering to life, it becomes something that life itself, through you and me and everyone who listens, has managed to see about itself.